Alrighty, so today I want to talk about kinetic energy, or KT. Some people will also write it KE, and I want to talk about how that affects reaction rate. Now, this can also be called Maxwell-Boltzmann distribution, and we went through some graphs, and I'm going to show you some graphs and kind of some stuff that happens. But first, I'm going to talk about the general idea, and it's that 1/2 KT, or excuse me, so kinetic energy equals 1/2, oop, woo, 1/2 mv squared. And the idea is that this kT also represents temperature. And because temperature is the average speed, because this is average speed, that means not all the particles are moving this fast. And then if we change these factors about a particle, then if the temperature doesn't change, then by changing these, this kT will change, which will then change our reaction rate. That's the general idea. So I'm going to look at increasing or decreasing the kinetic energy, which would also be the same as increasing or decreasing the temperature. We're going to look at increasing and decreasing the mass of something. And then the velocity is really what happens when we increase the temperature usually, because we don't change that. So we're going to change the M and we're going to change the V, see what effect that has on this and what that does to the reaction rate. So first we're going to vary the speed of it. So vary the temperature. So I'm going to draw a curve. This is going to be particle speed, SPD, particle speed, and here we're going to have particle number. Oh, nope, I've switched those up. So here we're going to have particle number, and here we're going to have particle speed. I think that's right. So here, and the curve is going to look like this. Oh, nope, I was right the first time. My bad. It is particle speed, and this one is particle number. And so this would be like 1,000, and this would be like 0, and in the middle would be 500. And these would be different meters per second. So 0 meters per second, 100 meters per second, 200 meters per second, the particle speed. And so what this is showing, the general idea is that just because the average temperature would be around here, you have some particles that are moving faster than that, and you have some particles that are moving slower than that. But the most amount of molecules, the area here, is going to be at the average piece. Once again, talking about the average speed. We could also talk about on these graphs a line if we drew it. If this was the activation energy, then only the molecules up here would be able to react. So to get more molecules over here to have the reaction, we could increase the temperature, or we could lower the activation energy, and we would do so by adding a catalyst. And this catalyst in a human body looks like an enzyme. And so like salivary amylase in your mouth starts the digestive carbohydrates. The catalysts take this line and push it this way. And by increasing the temperature, we take the number of particle speed. And we literally, I'm going to draw another graph here. We have particle speed here. And I have particle number here. And we take that, this is our normal distribution. And by adding heat, see how more of them moved this way. So this would be at like 100 degrees Celsius, and this would be at 300 degrees Celsius. And so that's how we could represent that, just seeing this shift. So that's what happens when we adjust the velocity or increase the temperature. Because by increasing the temperature, we're adding kinetic energy, but we're using the same molecule, so the velocity has to go up. And this velocity here is squared. So increasing the velocity will have a bigger impact on increasing this kinetic energy rather than increasing the mass. based on this equation. So I want to take a look at increasing the particle mass. So I'm going to draw that over here. Draw my lines. I have particle mass, or particle speed, and I have particle number. But I want to draw a line with helium, and then argon, and then krypton. I'm also going to reference my periodic table to make sure that I have it at the right thing. So helium, argon, krypton. So notice krypton here is the lowest, which means it is the most massive. So if they're all at 100 degrees Celsius, the helium, their particle speed, helium would look like this, argon would look like this, and krypton would look like this. And so just notice that krypton is lower because it has more mass. So if they all have the same kinetic energy, which is 100 degrees Celsius, and kT equals 1/2 mv squared, 1/2 mass times velocity squared. Because this mass goes up, the velocity goes down, which is why we see that the heavier elements like krypton and argon have lower average particle speeds at a given temperature than helium when doing this. So that's kind of the lens of kT and reaction rate. We increase the reaction rate when we push more molecules up over this activation energy. So the higher this is, the more collisions there are in collision theory, and these are the ways that you can manipulate that. So I hope that was helpful. I know that was a lot, but I hope that was helpful.